We had enough time to get through it. There are a lot of learning targets. Some of them are redundant from what we did in the modeling last time. Where's my mouse? So, we'll get rocking and rolling here. Here are the learning targets for today. And the first couple, we need to spend some time understanding the layers of the atmosphere. It's just kind of a fact-based, need-to-know sort of thing, so that we can understand and orient ourselves around this whole space where climate and weather takes place. So the spatial elements are kind of key. We've already talked about unequal heating of the earth and seasonal variations, and a few of the drivers that are responsible for the convection cycle, which are density and gravity. And then we have a whole bunch of things that we're going to knock out over the next coming days, which is the rotational energy of the Earth and how does that interact with climate and weather, and then understanding patterns of ocean circulation and some of the other major drivers or major climatological forces that help us understand why do we have these climates at these places on the Earth. Here's how you'll know that you really understand this topic, by the way. When you're able to get a latitude and longitude from any place on the Earth and tell me what environment you can find on that place. So we're going to hack from a conceptual standpoint. It won't be like memorizing all these places on the Earth, but you'll be able to say, okay, this is there, and because of this latitude and longitude, this is what I know about this place. And you can figure out. That's the truest test for I really understand the convection cycle, the convection cycles across planet Earth and how they drive Earth systems, which will also help us understand, okay, this interaction of the abiotic forces with the biotic forces. I really like this graphic, and what you can see, this is on loop of about 1 week, and it's showing the movement of air particles. So convection cycle, if you remember, is not the movement of energy through direct transfer, that's conduction, but it's the movement of particles from point A to point B. And so you see there's some really unique patterns here. And you can see almost the outlines of continents, and you can see a little bit about where the oceans are. So the fact that Earth is varied in terms of what surfaces it has is one key thing that helps drive climate and weather, because energy movement from the ocean to the air versus the land from the air, those have differences, but also because of the rotational energy and the seasonal variation. But we have these banding patterns. Everything in the warm colors are air that's moving really fast, and everything that's in cool colors is air that's moving slowly. Feel good? All right, let's get into it. Just a review from last time, just so that we can understand. I feel like I always want to start on home base one. You've already seen this information, but the energy on the Earth comes from the sun in the form of radiation. That energy heats up or excites a lot of electrons that can no longer hold the energy, and then the heat energy that comes from the Earth is conduction. So we're using heat energy direct transfer into air molecules, but once we end up in air molecules, or in water molecules, especially in the ocean or bodies of water. Both of those have properties of fluid dynamics, and they're driven by density and gravity, which is what we call convection. Feel good? Nothing new here. All right. Nothing new on this slide either. Just to point out that there are certain areas of the Earth at certain times of the year that are facing the Earth or the sun more directly. The more direct the energy is from the sun, the more heat energy you're going to have in that area. Somebody turn back to our notes from the other day and just give me the definition. If I have a lot of energy, so energy is a quantity, if I have energy, what can I do with that? What is our definition for energy? Yeah.
The ability to do work.
The ability to do work. So we're talking about climate and weather, and think about, well, what does work look like in terms of climate and weather? Here's a lot of energy. What are we going to do with that energy? And not we as people, what actually occurs, right? So the only thing that's I want to point out here, just to make sure we have it, is the molecules in convection. It's the actual molecules that are moving, and that piece is going to be really important. So it's movement of actual molecules. That can be compounds like CO2, diatomic nitrogen, N2, diatomic oxygen. It could be H2O. We're talking about the movement of actual molecules from one place to another place. Now we'll get into it. I want to spend about 90 seconds on this, and there's a key skill that I really want to keep improving. We've started this a little bit, but we're gonna keep driving it here. So the first is, just take a second to interpret this graph straight from the textbook. To help break down the graph a little bit in case it's hard to see, this is temperature, -0°C way over there. And then we have a couple breaks in the graph because on the far side over here, it's 1700 degrees Celsius. So from negative to 1700. And then this is altitude here from 0, which is the surface of the Earth. The exosphere there, that's what we call space, synonym for space. So the first thing I want you to do is list the layers of the atmosphere and then take some time to characterize the relationship between temperature and altitude. And you'll notice this is a unique graph with some unique attributes. So the characterization likewise should be somewhat complex. Here we go. All right, are we ready to do it? Tell me a little bit about this graph for number 2 here. So what can we understand about this graph? A good characterization, by the way, should be so explicit that someone else should be able to read what you wrote and draw the same type of graph. So that kind of exercise, when you see a characterization of a data set, that's the type of level that I'm hoping that we can achieve. So let's kind of break it down as a group, because this is a complex graph and we didn't need much time. What can you tell me about this graph? Relationship between temperature and altitude. Yes?
It doesn't follow, it's like one, it's not linear really, it sort of squiggles a little bit.
It's not linear, it has kind of a squiggle thing. That's good.
Very scientific.
Yes, that's a great start. What else? Yeah.
Eventually, as altitude gets to a certain point, the temperature increases.
So eventually, as we get to a certain place, the squiggles are done and we see something else happening. And what point is that? And what layer of the atmosphere is that?
Thermosphere.
We got it in the thermosphere. And where?
120 kilometers or so.
About 120 kilometers. We notice that it just starts going up from there. And what type, if you were going to talk about the line from 120, which is this point here, and up from there on the y-axis, or the value axis, what does that look like?
Exponential.
It's exponential, right? And is it a positive exponential or a negative exponential?
Positive.
Positive. There's some type of limit, right? Okay, very good. What else can we see? What else can we see? So we broke down most of the graph. What about the rest of it? Where's the highest temperature? The thermosphere. And then where's the next highest? So the lowest is about negative 70 in the thermosphere, and then the next highest, or the next lowest, sorry, is around negative 70 or so, and that's right here in the stratosphere, right? And then there's a big point where it goes up and it almost peaks out at about 0 degrees between the stratosphere and the mesosphere. And then we have way over here, it starts out at about 20 degrees and it gets cooler between there. So that's the kind of characterization that we'd like to try to get to. Again, it's our first time and it's a complex graph. But there are a few key things that I want to understand here. So the thermosphere, it has this name, and the variation of temperature is the widest, right? You're talking about from about negative 75 degrees Celsius all the way to 1700 degrees Celsius. It's a huge variation. It's also a huge amount of space. What I like about these layers is there's some kind of key thing that's happening in each one of the layers, which is why scientists gave it a name for that layer. But there aren't like actual layers of air that are stacked up. It's much more blurry lines between, and eventually we just end up where we're in space and we stop calling it our own atmosphere and we start calling it something else, which is the exosphere. There are two layers that will come up a lot, and I want to make sure that, so when I say these layers, you know exactly where I'm talking. The first layer is the troposphere, which is the space where we're all breathing. It's from the surface of the Earth until about 20 kilometers. How high is that? Does anybody know where airplanes fly? 38,000. At the highest cruising altitude, it's about 30,000 to 38,000, depending on the aircraft and the distance. But there, if we want to convert that to meters, because that's feet, and we want to put it on this graph, where do we end up? What 38,000 feet, how many meters is that? 11,000 meters. And how many kilometers? Because this altitude graph is on kilometers.
11 kilometers.
So 11 kilometers. So let's check it out. That's about right here in the middle, right? So when you're standing on the Earth and you look up and you see the tiniest airplane that's not landing in St. Louis, but it's cruising over us, that's about halfway between where you're standing and the edge of the troposphere. Okay? The other area that really comes up and is referenced a lot is the stratosphere, which is the layer directly above the troposphere. And it has this key thing that they called out here that's really important, peak ozone layer. And because it's not drawn in a way that makes it really understood, it's the floor of the stratosphere is where the ozone is. So the ozone layer is not at the top of the troposphere, it's at the bottom of the stratosphere. Does that make sense? What do we know about the ozone layer? There's a hole, yes. What else do we know about the ozone layer?
Like blocks radiation.
It blocks a lot of solar radiation, keeps a lot of harmful rays from reaching the Earth. What else? Maybe one other thing. When we say block, what do you think that means in terms of energy? It's reflecting it, right? Those two things are good enough. Okay, so that's what we're talking about, and you'll notice it gets kind of cool, and then because of the actual particles that are out here, we see some complex things happening with the temperature. But those are the two main things we want to understand. Feel good about layers of the atmosphere? Great. Simple stuff. Memorize it. Get it in your hearts. Remember it. A key term that we've seen before, and I know it's a little bit redundant, but just to bring it back, and I like this figure from the textbook, surfaces of the Earth reflecting energy at different rates depending on their material. And so what I like about this graph from the text is it gives you some percentages. So things that are very reflective, like fresh snow, reflect about 80 to 95% of the energy, where things that are really absorbent of the energy, like asphalt, only reflect 5%. So they're absorbing a lot of that energy. What I also like about this graph is you see there's a major difference between the amount of energy that's reflected if it's land mass. So take all of these and compare it to water. Water is 10 to 60%, but it depends on the angle because of the properties of water. And Earth, terrestrial land, is much lower. It's 5 to about, at the most, 20%. So water is more reflective, generally speaking, and that makes sense, right? You've seen that as a normal phenomenon. Okay, good. Okay, so the next thing that I want to talk about, and there's two key terms kind of embedded on this, so you don't have to write all this information down as a stepwise process, but I kind of like the way that this appears as a sequence of events. So we have this thing called adiabatic cooling and adiabatic heating. If we have air molecules that are near the Earth and we're transferring a lot of heat energy towards those air molecules, what is going to happen to the air molecules? If I have air molecules right here and the floor is extremely hot, what's happening with these?
They're going to heat up.
They're going to start heating up. And what does that look like in a molecular sense? They're moving fast, so the particles are starting to move. They have kinetic energy. And what's going to happen next? Where are they going to move fast to? They're going to start moving away from each other. And then because we used to be close together and now we're far apart, what's true? Less dense. And so then what's true?
It's going to
more dense stuff will push down, they'll be pushed up.
There, more dense stuff is going to be pushing down, and the less dense stuff is going to rise. So there's going to be some simple displacement that's taking place. We call that process of the heat molecules moving up into the cooler space. That's adiabatic cooling, because what is the next thing that's going to happen? As we get farther away from the source of heat, which is the Earth, what's going to happen to the molecules?
It's going to cool again.
They're going to get cooler and become what?
More dense.
And so the process where the molecules are moving away from the Earth is called adiabatic cooling. Now the reverse is also true, so we have some displacement going on. The cold, dense particles, let's break that process down. What's happening with those? Not much movement, not much kinetic energy, right? And so they used to be spread out, and now they're getting packed together. And via the agents of change for convection cycle, which are, what are they again? Density and gravity. So what's going to happen with those? They're starting to descend and fall towards the Earth. And as they fall, what are they getting closer to?
The heat source.
The heat source. So as the cool particles fall, they're going to start heating up. We call that adiabatic heating. This is a really interesting phenomenon. You can use it in humidifiers and all kinds of things. Let's go back to our definition that we had before. Energy is the ability to do work, agreed? So if we have warm air particles that can move around, one of the things those warm air particles can do is lift water vapor. So we have water molecules that are in gaseous form, and they're much heavier than the other air particles, and they're moved up because the air molecules through kinetic energy are pushing them up. But as they move up, we start to lose energy, and we become more dense. That process of becoming more dense is going to bring the water molecules together, which is this phenomenon we call condensation, right? And eventually the water molecules are going to be so dense that I don't have enough energy to hold them up anymore. And so they get released, which is precipitation. So now we're already starting to understand this relationship between one key thing, which is the sun's energy, and convection and its relationship to rain being formed and falling towards the Earth. So this graph just kind of shows what that process looks like. So as the temperature goes up, we start to condense the molecules together, and the temperature of air saturated with water vapor at 1, and this is where it's going to fall. So as the saturation point goes up, because the molecules are lifting it and they're getting cooler and they're compacting together, that's where we're actually going to get clouds being formed. Okay? Actually, I made a different graph that shows these kind of together. So this graphic I really like. Let's just take a second. So we have warm air here, and it's being warmed because it's near the surface of the Earth. It's lifting air molecules. The air molecules are moving up because they're becoming less dense. They're doing a lot of work, which is lifting water molecules. They get condensed. They can't be held anymore. The water falls. What you'll notice here is the air continues to ascend because it still has enough energy to become dense itself. It just can no longer hold water. And then you're going to get cooler and fall back towards the Earth and get warmer. And then the process is going to repeat in a cycle. Does this make sense so far? Yes.
So do they get cooler even though they're technically closer to the direct radiation?
They do. So the sun's energy transfers some of its energy and excites electrons onto gas particles themselves, but that's on a magnitude of scale lower than the heat transfer from the Earth to the gas via conduction.
Okay.
So yes, and it's because the gas particles are so spread out.
Okay.
Right? Okay, does that make sense? So this process happens faster over land than it does over water because we have more energy, and it happens much more concentrated in places where the Earth is facing the sun more directly, like the equator. All right. Feel good about this so far? This is like just the next sort of level, and then we're going to get into increasing complexity here. Okay. This whole thing we call the convection cycle because convection is the energy source, and it happens in a predictable and cyclical nature, so we call it a cycle. Just to orient ourselves, because this graphic is a little strange. It's from the textbook, and the textbook wants to show you what the atmosphere part looks like. So it's oriented it so the globe looks like this. So we're used to looking at the globe like this, but it looks like this. And it looks like this for a few specific reasons. So here, just to understand it, is the equator. And then this is 30 degrees north, and here is 30 degrees south, which, if I'm going to put my fingers on it, 30 degrees north is about here, and 30 degrees south is here. So this is over a huge span of latitude. Does this make sense? All right, so this is happening on a macro scale. What you just saw on the previous picture was a small scale of a weather pattern over a mountain, for example. But a climatological pattern is bigger in terms of space, and it's longer in terms of time. Let's break it down. So at point 1, why would that be the main point of focus here? What is true about point 1 that really matters, Ethan? What's happening at point 1? We see rain, but let's just think about the Earth. So this is called, well, let's just focus here. This is the equator. Why do we care about the equator? What's true about the equator? It gets the most direct sunlight. And how varied is that sunlight energy across the year?
Not much.
Not very varied. So it's getting many days of lots of direct sunlight, many hours of direct sunlight. And so what can we do with a lot of sunlight energy?
Warm a lot of air.
We can warm a lot of air, and what can we do with a lot of warm air? Move what? Move a lot of water. All right, so now, think about this. What kinds of ecosystems do you find at the equator? What do they look like? It's rainforests. And how does it feel when you're in a rainforest? If you've never been, just imagine. It's humid, and it's hot, and it's a lot of rain, right? So there's no mystery to that. All right, so let's keep this going. So the heat energy is the most intense here because of the direct sunlight and the number of hours and days. And we're moving air particles up, and those air particles are moving water particles that are condensing. And then eventually we get to a point where you can no longer carry them, and we dump. And the rain, there's a ton of rain happening here all the time because this process is just repeating in a very small micro sense, right? But the air particles continue to move up until point 3. Why do we not have, so if we have density and gravity carrying things up, and I'm just going to call this point A, and we'll call this point B, why don't we have adiabatic heating occurring where the air molecules are just coming right back down from B to A? Why do they go, according to this drawing, from B to C? Why do you think? That little movement thing is really,
Yeah.
sorry. I don't know why it needs greased. Why wouldn't we just have the particles falling back down? Yeah.
Because the Earth's turning.
So we have some rotational energy from the Earth. That is part of it. But what else? Yeah.
Is it because it's going through an area where the atmosphere is drier, like the Earth is drier?
So an area to where the Earth is drier, that could be part of it. Yeah, Spence?
Because like the air cycle doesn't have to carry the water.
So the air doesn't have to carry the water, which is true. So let's just track this again. This is really good. We have A, we're bringing it up, and we're hot and moist, and then we're becoming dry and cold up at point B. So these titles, dry and cold, it's dry because we lost all the water, and it's cold because we're so far up in the atmosphere, and adiabatic cooling has happened this entire time. So by the time we get to point B, we're now cool and dry. Why don't those particles just descend right back down from B to A?
Is it because there's still the warm air or hot air coming up, so it has to get out of the way?
Yes. So we have displacement occurring because there's so many air particles moving up. Because what's the driver for this whole thing?
Gravity. It's the heat at the surface.
It's the heat at the surface and then gravity and density once we get to these air molecules, right? So we have so much heat energy here that we're constantly pushing the air molecules up. And by the time they get to B, they can't just go down because there's too many guys picking them up. So where do they move? They move away. And you'll notice this is why we end up with a mirror image, and this is kind of an important point. So again, here's the equator, and you'll notice there's a mirror image of this thing on either side of the equator. And those molecules get up, and they move away from each other because there's a high density of molecules there, and they can't go down, so they move away. And they move a very far distance. They go from 0 all that way. It takes a long time for them to fall back towards the Earth. Does this make sense so far? Okay. So now at C, check this out here. We have adiabatic heating taking place as we go from B to C. So the molecules are slowly getting warmer as they fall. By the time they get to the surface of the Earth, they're hot. And because we lost all our water in between point A and B, we're still extremely dry. So what kinds of things, and you'll notice this on the graphic, this is Africa here. What kinds of environments do you notice at 30 degrees north and 30 degrees south? They're deserts because they're dry and they're hot. Does this make sense so far? Good. All right. Few more minutes to go. Okay. All of these areas, Joe, sorry, go ahead.
Going back to the graphic, what makes the molecules then move from C back to A?
Yes, so why from C to A? This is a great question. Let me solve that here in the next one. That's a good one. I'll get to that. All right, so you'll notice there are about 6 different convection cycles on the planet. If we just had the sun sitting in one position and the Earth sitting in another position and neither one of them were moving, we would have only one convection cycle going from the equator out here because it would be a really controlled mechanism for the sunlight. But because we have seasonal variation in the axis of the Earth and everything we saw downstairs, and we have different surfaces with different albedos, we end up breaking it into different regions. And so we actually have multiple convection cycles taking place. And so we have one convection cycle here between 0 and 30 degrees. And we have another one between 30 and 60 degrees. And then a final one between 60 and 90 degrees. Each one of these has a name that we'll get to in a second. So these big circular airs, or circular arrows here, the reason they're shown like this on this representation is because we're looking at the movement of air particles into the atmosphere, just like we saw on the previous graph. So here is point A, here is point B, and way over here is point C. Does this make sense so far? Okay, so these circles are showing in the atmosphere, and these arrows that are flying all over the place are showing the movement of air particles across the surface of the Earth, which we're going to have here in a little bit. And I know it's a lot of flying arrows, moving around, but so stay with me. So the heat energy is causing the particles to move up. We end up with a low pressure area. This one, I don't know why this showed up. It's black here. It's supposed to say high pressure, sorry. And then low pressure out here. Gravity and density is making the cold particles fall back towards the Earth, where we end up with a high pressure area, and then we're moving. So this is the point. Who was the person who asked, why do they go from C back to A? Who said that? Okay, why do they go back from C to A? If you remember, we have these things called ideal gas laws. And pressure is the molecules hitting, usually think about that inside of a container. So the molecules are moving, and we can increase the pressure if we increase the temperature, so more kinetic energy, more collisions happening. We can also increase the pressure by putting more stuff in there, so higher density, right? And so if we look at this, we have all of the air particles moving up into the atmosphere. And so that movement is, we end up with fewer moles here of stuff, because we've just moved all those particles from A to B. And then when they come out here and they move down, we have a high density here, because we've just added a whole bunch of molecules here that didn't used to be here. And there's a vacuum here because of the movement, and so we have this circle happening, and we're moving from high to low pressure. In the same way that we have things always going from high to low energy, we have things always going from high to low pressure. So we move from B or C to A. Yes, Spencer.
Why is it the winds like going different directions? Is that
Why do they go like this
Yeah.
and then sometimes like this?
Yeah.
That's going to be the business of our work starting tomorrow, which is this phenomenon called the Coriolis effect, because we have to implement the rotational energy from the Earth. Why are you laughing about Coriolis effect?
This is from like sixth grade.
Yeah. Did you understand it in 6th grade?
Kind of.
Good.
It's like
Well, we're going to learn a lot more about it. We're going to take the entry-level college class version of the Coriolis effect, and with a little luck, I won't get electrocuted by my record player. Just a little ahead of time for a future class. Okay, so how do we feel about this so far? Questions on this? Yeah.
Why are the certain surface areas high or low pressure?
So the surface area near the equator is low pressure because we're moving all the moles out. And when we move the moles of air particles out, we decrease the pressure, so there's fewer collisions taking place. And the reverse is true here. As they fall, we've taken a bunch of particles and we added them to this space here. And so they're high pressure, and the vacuum created here is going to be pushing these back towards the equator.
Okay.
High to low pressure. Sound good? Feel good? Feel like I have one more thing. I kind of want to keep both classes on a similar spot, but I'm going to give you this so that you guys can have it. Actually, let me bring these in. So each one of these convection cycles has a name. So the one that's nearest the equator, from 0 to 30 degrees, we call that the Hadley cell. The convection cycle between 30 and 60 degrees, we call the Farrell cell. And those two are weird, and I don't have a good mnemonic device for remembering which one is which. But the polar one makes sense. From 60 to 90 degrees is the polar cell. And this last point here that I'll make before we kind of end it for the day. Does anybody have questions about any of this so far? No. Okay. This last point here in the red box that I'll just mention is the energy at the equator is so intense and so great that the residual energy from the Hadley cell is where the energy for the Farrell and the polar cells come from. And so if you look at this, these cells turn on each other like gears of a clock or that kind of thing. So the Hadley cell is responsible for all the other movements. So it's going up like this, and residual energy from it is powering the other one. It goes in the reverse direction. And the residual energy from the Farrell cell powers the polar cell and so they turn on each other like gears. Yes.
I have a way to remember that the head was up close to the Ferrell Stone. The second.
All right, let's hear it.
Will Ferrell's from the Ferrell Stone. Like that area.
From North America.
Yeah.
Do we know that's true? I don't know anything about Will Ferrell. What if he's born in
California?
Irvine, California? There you go. Who's a Will Ferrell fan in here? Nobody.
Sure.
A couple.
Nobody.
So I just saw this thing the other day in the news. They were going through and they had done an analysis. This team had done this analysis on the most quoted movies of all time. And anybody want to make guesses on what the most quoted, like memes, Twitter, everything? They computed all of this data.
The Office.
No, movies.
Are these gonna be like Will Ferrell movies?
It's gonna be
Not Will Ferrell's total movies, but
I'm guessing
I'll give you a hint.
there.
I'm gonna say Talladega Nights is gonna be up.
Oh yeah, I
Same.
didn't even think
I was
about
gonna
that.
say
Yeah.
Number one, anybody want to guess on number one? It's an old movie.
Forrest Gump.
Like
God.
Older than that.
Old Fiction.
Forrest Gump's not that old. Older than Neil.
Ferris Bueller.
That's the same era as Forrest Gump.
So like, are we
It's
talking
a
like
different era than
50s
Forrest
and
Gump.
60s or like earlier than
Older.
that?
Well, 50s.
Okay.
I don't know.
Yeah, that's a hard one.
Frankly, my dear, I don't give a damn. Anybody?
Oh, that's the movie with the plane.
Oh,
Airplane?
No.
No, not Airplane.
That's the weirdest.
Casablanca's number
Yeah, it's
one.
Casablanca.
Oh.
Guess what's number two? This is insane. Mean Girls.
Oh wait, I was gonna say that.
Mean Girls, and then Anchorman is number three, and then there's a whole bunch of other stuff. I do think Forrest Gump was in the top 10, but I got all broken up on it when I saw Mean Girls. I was like, come on, man, Mean Girls. Although, gotta give it credit, Mean Girls into that.
I think it's just very quotable too.
It's
It's not
very
like just like the
quotable.
movie. It's like it's just there's a lot of like.
So here's what we're gonna do tomorrow. We're gonna do some modeling with the convection cycle. We'll do a little walkthrough just to make sure we really understand this. And then we'll do the Coriolis effect. And we'll have one other thing to do on the convection cycle before we end. And then we'll talk a little bit more on Friday about ocean currents and the movement of water. But we have to understand all this about convection cycle first. In the atmosphere before we can understand it in the ocean. And then after that, we'll do a little bit of watershed and we'll be on for the test. Just for, since this group, you guys will be cheated on extra time with me, but just to know for reference, you'll take, the format of the tests are 100% on Canvas.